So, isahin na natin what are the properties of fluid. Yeah. The first property that we are going to discuss is the mass density. Mass density is defined as the ratio of mass to volume at a point given by this equation right here. That's mass over volume. So mass can be in the unit of kilogram for SI, slugs naman kapag English system. Volume, it is in cubic meters or in feet, or in English system, cubic feet. So we have an equivalent unit for your mass density of kilogram per cubic meter. Pag English system naman, slugs per cubic feet. Yan. Kapag gases naman ang concern natin and we want to determine the mass density, okay, we have ideal gas where its density can be found from the specific gas constant, yung R, and ideal gas law. So this is your ideal gas law. P is equals to rho pala. Rho is your symbol for mass density. Is equals to P over RT, where P is the absolute pressure of gas and T is your absolute temperature in Kelvin, and R is the gas constant in joule per kilogram degree Kelvin kung naka SI units. Then, specific weight or unit weight. The gravitational force per unit volume of fluid, or simply the weight of per unit volume, is defined as the specific weight. So we have a symbol of gamma. Okay, kung given yung unit weight, yung weight, okay, which is in the unit of Newton or in pounds, okay, per unit volume, yan din yung inyong unit weight. Or simply, if we have the mass density rho, multiplyan mo lang ng g. Okay, yung acceleration due to gravity para maging unit weight siya. Okay? Kasi nga, kung babalikan natin, weight is equals to what? Mass times g. So, therefore, kung ang unit weight is just equals to weight over volume, okay, ang weight, diba, is mg over v. At kung babalikan natin, mass over volume is your mass density. Kaya, nag-arrive dito. Okay. So, this can be used as your formula for unit weight. Or we can also use this one. Depende sa given. Specific volume and specific gravity. Specific volume is just yung 1 over rho. Okay, parang reciprocal nung inyong mass density. So 1 over rho, yung specific volume. So syempre yung unit niyan mababaliktad. Kung kilogram per cubic meters yung unit mo for the mass density, pag hinanap yung specific volume, that's cubic meters per kilogram. And the specific gravity is the ratio of the specific weight of a given fluid to the specific weight of water at the standard reference temperature of 4 degrees Celsius. So, ito yung standard natin. 9.81 kN per cubic meter. Ang specific weight ng water at 4 degrees. Yan. So, kunyari, meron kang unit weight of any fluid, divide mo lang yan ng unit weight of water, which is yung standard na 9.81, okay, that will be your specific gravity. But if it is specified there, yung temperature at 20 degrees, ang gagamitin nyo na unit weight of water should be 9.79. Okay, kapag 20 degrees Celsius, ang specified temperature, ito ang gagamitin yung unit weight of water. So, apply na natin to sa mga sample problems. lahat ng na-discuss natin on these properties. First, we have the mass density, mass over volume, ideal gas, P over RT, and we have a specific weight or unit weight. It can be weight over volume or mass density multiplied by G. Then we have the specific volume, 1 over rho. Specific gravity is the unit weight of the fluid divided by unit weight of water. Okay. Example. Sample number 1. This is a past board, November 1995. If we have a given of volume, which is 5.6 cubic meters, and the oil weighs, okay, it's a unit of weight, 46,000 newtons. What is the unit weight, density, and the specific gravity? Letter A. What is the unit weight? The unit weight, symbol gamma, is just simply weight over volume. We can also use the mass density, rho times G, but we don't have a given of mass density here. So we will take advantage of the given 46,000 and volume of 5.6. So, directly substitute it here, 46,000 newtons all over 5.6 cubic meters. Please compute the values. Okay. Gamma is equals to 8214.286. That's Newton per cubic meters. That's the answer for unit weight. That's for letter A. Letter B. What is the density? What is rho? Going back on the lecture, unit weight is mass density multiplied by G. So if we already have a unit weight, gamma, okay, we can just simply divide both sides by G so that unit weight over G is your mass density. Okay, so let me rewrite that. That will be 8214.286 Newton per cubic meters to be divided by 9.81. G is acceleration due to gravity. We are in SI units. So that's meter per second squared. Okay, just to check the consistency of units. Okay, Newton is equivalent to a unit of kilogram meter per second squared. Okay, so if you have this unit, Newton per cubic meter, so you divide it again by cubic meter, all over meter per second squared, what unit will remain? Okay, the unit that will remain is, okay, so this will be cancelled out. This meter square, second squared will be cancelled out. So the unit that will be remaining is kilogram per cubic meters. Okay, so make sure that our unit for unit weight before dividing it by G should be in Newton per cubic meters. So dividing the two, 8214.286 is divided by 9.81. Okay. That's 837.338. That will be in kilograms per cubic meters. That's for letter B. That's the density. Then C. specific gravity. Specific gravity, SG, is equals to unit weight of the fluid divided by unit weight of water. There is no specified temperature of the water here at 4 degrees or 20 degrees. So we always use the standard, which is at 4 degrees Celsius, which has an equivalent of 9.81 kilonewtons per cubic meters. Okay. So the unit weight of the fluid that we have determined here is 8214. That's 8214.286 Newton per cubic meter. While the unit weight of water is 9.81 kilonewton per cubic meter. So you have to memorize already that the unit weight of water should always be 9.81 if there is no specified temperature here. Okay, in the given. We use the standard at 4 degrees Celsius, and our unit weight for water will be always 9.81 kilonewtons per cubic meters. So as you can see, when we divide it by, when the unit weight of fluid is divided by the unit weight of water to obtain the specific gravity, okay, our units are not the same. This one is in newtons per cubic meters, while the unit weight of water is in kilonewtons per cubic meter. So you have to convert it into newtons per cubic meters. So to convert 9.81 kilonewtons per cubic meters, converting it to newtons per cubic meter, just multiply 1000 newtons as your conversion factor. Okay, kilonewtons, sorry. That 1 kilonewton is equivalent to 1000 newtons. So this will be cancelled out. That will be 9810 newtons per cubic meters. So this will be divided by 9810 newtons per cubic meters. This will be your specific gravity. So the specific gravity is equals to 0.837. This is your answer. Next slide. Another example. A certain liquid has a unit weight of 55 kilonewton per cubic meters. We are required to determine the density, specific volume, and the specific gravity. So let's write first the given, which is unit weight of 55 kilonewtons per cubic meters. Determine the mass density. The mass density, rho, is what? From unit weight, that is equals to mass density multiplied by G. We can take advantage of this solution. Since we already have a given unit weight, okay? So to obtain the mass density, just divide both sides by G, or the mass density is unit weight over acceleration due to gravity. But our unit for the unit weight should be in newtons. Okay? This should be in newtons per cubic meter. So again, we convert it again. That 1 kilonewton is 1000 newtons. That's your conversion factor. So we have 55,000 newtons per cubic meters. That's your unit weight. So 55,000 newtons per cubic meters is divided by 9.81 meter per second squared. Okay. Again, to review the units, why we use Newton. Okay, this will be your units. Newton per cubic meter is divided by meter per second squared. Okay, Newton has an equivalent unit of kilogram meter per second squared divided by cubic meters. Then you divide it again by meter per second squared. Okay, so this will be cancelled out again. Second squared is cancelled out. What unit remains is kilogram per cubic meters. By dividing the two, 55,000 divided by 9.81, 5606. Okay, wrong. Yes, 5606.524. That's in kilograms per cubic meters. That's the answer for letter A, the mass density. Letter B, calculate its specific volume. The specific volume is what? Specific volume, okay, going back to the lecture, that's just 1 over mass density. So if we have mass density of 5606, so 1 over 5606.524 kilogram per cubic meters, the specific volume is equals to 5606.524 equivalent to 0.000178. Okay, that will be in cubic meters per kilogram. Okay, the units will be inverted. That's for specific volume. Compute its specific gravity, SG. Okay. For the specific gravity, we can use unit weight of the fluid divided by unit weight of the water. There's no given temperature here, so we will use unit weight of water of 9.81 kilonewtons per cubic meters. Okay. But since the unit weight of fluid here, we already have a given of 55 kilonewtons per cubic meter. We can already use that. 55 kilonewtons per cubic meters is divided by the unit weight of water, which is in standard temperature 9.81 kilonewtons per cubic meters. So the specific gravity is equals to 5.606. Okay. That's your specific gravity. Another example. What is the specific weight of air at 480 kilopascal absolute at 21 degrees Celsius? Then we have the constant of 287 joules per kilogram degree Kelvin. So we will be using ideal gas law here with the formula of rho, or the mass density, of P over R T. But take note that with these givens, our units must be consistent. Starting with the pressure. The pressure should be in Pascal, while R, joules per kilogram degree Kelvin, and the temperature should be in Kelvin also. So our units for this problem should be consistent so that the output or the required mass density has really a unit or a unit for mass density of kilogram per cubic meters. So let's review that, because what will be the equivalent of Pascal? What will be equivalent of joules, kilogram, degree Kelvin, and degree Kelvin? So from this, the degree Kelvin will be cancelled out, but Pascal is in Newton per square meter, While joules is a unit of work or force times distance, Newton meter, okay, over kilogram. So you can see Newton can be cancelled out and this can be added here, okay? Since when we divide fractions, we can multiply it by reciprocating the other, or in kilogram per meter. So when we multiply that, that will be kilogram per cubic meter, which is a unit of mass density. Okay, that's why we are to convert all the units depending on the given. Starting from the pressure, we have a pressure of 480 kilopascal. So we convert it into Pascal because this is in kilopascal. So the conversion factor is just 1000 Pascal is your equivalent for 1 kilopascal. So multiply 1000, this is 480,000 Pascal. Okay. While your temperature is in degrees Celsius. Okay. So what will be the equivalent temperature of 21 degrees Celsius to Kelvin? Okay. Our conversion is just simply adding 273. This will be 294 degree Kelvin. Then our units are already consistent. And we can now directly substitute that here on this general formula. Okay? Rho is equals to P over RT. P is in 480,000 Pascal to be divided by R, which is given 287 joules per kilogram degree Kelvin, and the temperature of 294 degree Kelvin. So rho is equals to 480,000 divided by 287 times 294. Okay, this will be your unit. It has a very low value, 5.689. 5.689. That will be your mass density, kilograms per cubic meters, using ideal gas law. Okay? Let's proceed. The bulk modulus of elasticity, another property of fluid. For the bulk modulus of elasticity, we have a general formula of negative delta P over delta V over Vi. Delta P is just simply your change in pressure. Okay? The final pressure is subtracted by the initial pressure. The delta V is your change in volume. The initial or the final volume is just subtracted by your initial volume. So that's your delta P. This is delta V. That's your bulk modulus of elasticity. And to determine the coefficient of compressibility, beta, is equals to 1 over E. So just take 1 over E for the bulk modulus of elasticity. That's your equivalent coefficient of compressibility. Okay. So memorize these formulas and apply it here on this problem. Okay. A liquid is compressed in a cylinder if it has an initial volume of 1000 cubic centimeters at 2 megapascal, then it is compressed having a volume of 990 cubic centimeters. Now the pressure is 2.6 megapascal. Let's compute the bulk modulus of elasticity, the percentage of volume decreased, and last, the coefficient of compressibility. Letter A. Going back to the formula to be used, E is negative delta P over delta V over V initial. Let's use that on the required problem in letter A. So E is equals to negative delta P over delta V over V initial. Let's solve first. What is delta P? Delta P is delta P is just the final pressure minus initial pressure, while delta V is your final volume minus initial volume. So we substitute that all here. Negative, the delta P is the final pressure is 2.6 megapascal minus the initial pressure is 2 megapascal to be divided by delta V. Delta V is your final volume. Your final volume is this one, 990 cubic centimeters, subtracted by initial volume of 1000, then divided by the initial 1000. So the unit cubic centimeters will be cancelled out. What unit remains is the megapascal. So directly computing all this, we have an answer of 990 minus 1000 over 1000. 60. This is 60 megapascal. That's the bulk modulus of elasticity. Letter B. Compute the percentage of volume decreased. What will be the percentage of volume decreased? So the percentage of volume decreased is just simply your delta V over Vi, but multiply it by 100%. Okay, to convert it into percent. So delta V over Vi is just your 990 minus 1000 over 1000, then subtract, multiply it by 100%. Okay, compute that. We have 990 minus 1000 over 1000 times 1. Negative 1%. Okay, that's the volume decrease. It decreased by 1%. Letter C. Compute the coefficient of compressibility. Okay, beta. That will be 1 over E. So, 1 over E, if the unit for megapascal, this is 60 megapascal, the equivalent unit of megapascal is what? Recalling Pascal is newtons per square meter. So if it is in megapascal, it means that is in meganewtons per square meter. Okay? So if we divide 1 over 60, our answer is in 0.0167. But the unit, concerning the unit, this will be reciprocated. Okay? Square meter over meganewton. That's your coefficient of compressibility. Okay? It is a measure of fluid's resistance to deformation under shear stress. Okay? Or we can say that it is the ability of the liquid to resist, to flow. Okay? It is the resistance of it to flow. Say for example, here, we pour water with less viscosity as compared to oil with a higher viscosity. So, comparing the two, same amount of volume to be poured out, okay? The water flows easily as compared to the oil, okay? When we are trying to pour oil, uh, the tendency is, the flow rate is very low as compared to water. Okay, water can easily flow on this beaker. That's because of its property, which is viscosity. There is fluid resistance here, okay, that causes it to resist the flow. So we have an absolute viscosity, which has a general formula of this one, and the kinematic viscosity formula of this one. Okay, so we can use kinematic viscosity when the liquid is already flowing. Okay, but all liquids have their absolute viscosity, and that's what we are going to determine here, or we are trying to solve in this discussion. Okay, so for the unit of viscosity, absolute viscosity, which is represented by a symbol mu, we use a unit of pound second per feet squared, or in SI units, we use Pascal second. We also have an equivalent unit of viscosity, which is also called as poise. So if we have a Pascal second equivalent of absolute viscosity, and we're trying to convert it into the unit of poise, this is your conversion factor. 0.1 Pascal second is 1 poise. Also, in this formula, we have the shear stress, which in the unit of pound per square foot, and Pascal. Then, with the use of absolute viscosity, and when the liquid starts moving, okay, we can still determine its viscosity using this solution right here for the kinematic viscosity, which is represented by this symbol mu. So mu is equals to mu over rho, or the mu is just your absolute viscosity divided by the mass density of the liquid. Okay? Let's apply that here on this sample problem. Given we have a temperature of 70 degrees Celsius and its viscosity, absolute viscosity, is given in the unit of poise. So, the water has an absolute viscosity given of 0.00402 poise. And the specific gravity, Sg, is 0.978. Determine its absolute viscosity in the unit of Pascal second. Okay? We are also required to determine the kinematic viscosity in meter per second squared as well as in Stokes. So first, let's convert the poise into Pascal second. That's the first requirement. Okay? So going back here, 1 poise is 0.1 Pascal second. That's your conversion factor. So, 0.1 Pascal second over 1 poise, when we multiply that to the given absolute viscosity, that will be equals to 0.00402 times 0.1 over 1. That's 0.000402 Pascal second. Okay, that's your answer. for the first question, which is the absolute viscosity in Pascal second. Then the kinematic viscosity in meter squared second. Okay. So the kinematic viscosity has a formula of mu is equals to mu over rho. So mu, using Pascal second unit of 0.000402 Pascal second, is divided by mass density of the liquid or of the water, but we don't have yet the mass density of water, given that it has a given temperature of 7 degrees Celsius. So if there is a given temperature, it means that we cannot use the standard mass density of the water or the unit weight of water. So we can determine the mass density of water by using its specific gravity of 0.978. Okay? Specific gravity of 0.978. As we recall, specific gravity is the unit weight of the fluid over the unit weight of water at a standard temperature. This is at a standard. But here, our temperature is at 70 degrees. So it means our unit weight of liquid here is at 70 degrees Celsius. That's what we're going to determine here. Okay? So therefore, the unit weight of the fluid is equals to, when we multiply unit weight of water to the specific gravity, that's your unit weight of the fluid, which is at 70 degrees Celsius. Okay? So we will use this to obtain the unit weight of the fluid. Okay? So let's solve that. So unit weight of the fluid is equals to 0.978 for the specific gravity, and the unit weight of water to be used at standard is 9.81 kilonewtons per cubic meters. So when we multiply the two, okay, at 70 degrees, okay, 0.978 times 9.81, 9.594. That's your unit weight. But what is required here is the mass density of the water at 70 degrees. So, going back again on our lecture, the unit weight is rho times G. So, rho is just unit weight over G. So, divide this by G, the 9.594, to obtain the mass density. So, obtain the mass density. Okay, let's separate this one. The mass density is unit weight over G. So 9.594 kilonewtons per cubic meter all over 9.81 meter per second squared. But wait, this is in kilonewtons, so you have to convert it to newtons. So I have a conversion factor of 1000 newtons is equivalent to 1 kilonewton. So this is your solution in obtaining the mass density of the water or of the fluid at 70 degrees. Okay. So 9.594, okay, multiply it by 1000 divided by 9.81. 977.981 kilograms per cubic meters. We will substitute that here. 0.0000402 Pascal second over 977.981 kilograms per cubic meters. So this will be your uh, kinematic viscosity. So our units are consistent. Okay. Just to review again the units. Okay, let me write it here in the upper left portion. Pascal second divided by kilogram per cubic meters. Pascal, again, is in Newton per meter squared. We have second over kilogram over cubic meter. And also Newton is in kilogram meter per second squared. So the units will be cancelled out, and what unit remains here will be in the unit of absolute viscosity, which is in meters squared per second. Okay, units will be cancelled out, and the unit that will remain is in meters squared per second. So dividing this to 0.000402 per 977.981, 4.11 times 10 raised to negative 7 meters squared per second. That's your answer for the kinematic viscosity in meters squared per second. While in Stokes, okay, we will just simply convert that. The 4.11 times 10 raised to negative 7 meters squared per second is multiplied by the conversion factor of 1 Stoke, which is equals to 0.0001 meters squared per second. Okay, 0.0001 meters squared per second. Sorry. 1 Stoke is 0.0001 meters squared per second. So this will be cancelled. Okay. So divided by 0.0001. This will be 4.11 times 10 raised to negative 3 Stoke. Okay. That's how we solve a sample problem on viscosity. So every liquid has its own absolute viscosity, but it will be different when it comes to its kinematic viscosity, depending on its values. Any question? For the next property of fluid, it is the surface tension. It is a material property whereby a liquid at a material interface, usually liquid or gas, exerts a force per unit length along the surface. Okay. That's why some of the insects can walk on water, okay, because of the surface tension. Okay. Yeah, that's your surface tension here. And it can be computed with this general equation for gauge pressure. So we have P is equals to 4 sigma over D. Sigma is your surface tension, D is the diameter of the droplet in meter, P is the gauge pressure, which is in Pascal. Then for the capillary, it is the name given to the behavior of the liquid in a thin bore tube. Okay. Usually there is a rise on the level of the surface of the tube when it is dipped on the liquid, and we call that as the capillary action. And again, surface tension is related to that. The rise or fall of a fluid in a capillary tube is caused by surface tension, and it depends on the relative magnitudes of the cohesion of the liquid and the adhesion of the liquid to the walls of the containing vessel. When we say cohesion, it is the ability of light molecules to stick together, while adhesion, it is the ability of dissimilar molecules to stick together. This is how it looks like if the liquid is too cohesive, or the tube and the liquid it has an adhesion effect. This is the example for that. So it will depend on the concavity of the surface of that liquid when put into a container or in a tube. When the liquid is too cohesive, it means that their molecules, okay, are too cohesive and they really stick together. Okay, the concavity of of the surface will be downward. Okay, then in adhesion, okay, the liquid stick on the walls of the surface of your container or on the tube. That's why, okay, there is slight rise on the liquid surface, but it is just the effect of the adhesion because the liquid is sticking. Okay, the two different material stick together, the liquid and the walls of the tube. So the concavity is upward. Okay. So to compute that capillary rise on the tube or any um, material that we put here with the specific diameter, um, we use this equation considering the effects of surface tension. So the capillary rise is equals to 4 sigma cos theta all over gamma d. So theta is your wetting angle. Okay. It is the angle tangent to this surface that is adhesive to the wall of the tube. Okay, when we compute or we measure that angle along the vertical, that's your wetting angle. Then the unit weight of the liquid, gamma, d is the diameter of the tube. Let's solve this problem. Sample. Determine the surface tension of water in a tube with 0.2 meter radius and wetting angle 0 degrees and capillary rise of 5 mm. The letter B, if the surface tension is in pound per feet, let's determine that also. And if we have a given wetting angle of 80 degrees, what will be your surface tension? So let's recall again the formula. This one. H is equals to 4 sigma cosine theta over gamma d. Let's write down first the given. For letter A, we have a radius of 0.2 meters. Wetting angle theta, 0 degrees. Capillary rise H is in mm, 5 mm. General formula is H is equals to 4 sigma cosine theta over gamma d. So we have a given radius, we have to find its equivalent diameter. Okay. Diameter is twice the radius. So therefore, multiply this by 2, its diameter is 0.2 meters times 2, that's 0.4 meters. Then, how about the units to be used? Okay. As we have a height capillary rise, which is in mm, while the other units to be used, which is for the unit weight of water, we have newtons per cubic meter, and the diameter is in meter, it is much better that we use a unit of meter for the capillary rise H. So let's convert this into meter by multiplying a conversion factor of 1 meter equivalent to 1,000. So divide it by 1,000. So this is 0.005 meters. So what is required in letter A is the surface tension of the water. So there is no given temperature here. It means that we will use the standard temperature of water at 4 degrees of 9.81 kilonewtons per cubic meters. So, again, it's much better to use newtons. So we convert this to newtons per cubic meter by multiplying again a conversion factor of 1000 newtons is 1 kilonewtons. So the unit weight is 9810 newtons per cubic meters. Next, let's determine the sigma or the surface tension. So let's isolate that variable there by simply cross multiplying this denominator on the left side and all the numerators here for and cosine theta as your denominator on the left hand side of the equation. So h times gamma d over 4 cosine theta. That will be your equivalent solution for this. So this is for letter A. Or let me rewrite this. This will be your solution. Then substitute h, which is 0.005 meters, gamma, the unit weight of the water, 9810 newtons per cubic meters, multiplied by d, 0.4 meters, to be divided by 4 cosine of theta, which is 0 degrees. 0.005 times 9810, 0.005 times 9810 times 0.4 over 4 cosine of 0. 4.905. Sigma is 4.905 Newton per meter, since meter will be cancelled out here. Then letter B, we convert that into pound per foot. So, sigma of 4.905 Newton per meter is converted to pounds. Okay, 1 pound is 4.448 newtons, while 1 meter is 3.28 feet. So this will be equal to, let me complete that again, it's 4.905 times, will be divided by 4.448 times 3.28. That will be 0. Okay, sigma is 0.336 pound per feet. This is the answer for this one. And for letter C, okay, letter C, we just replace the theta by 80 degrees. Okay, because here, theta is 80 degrees as required. So 0.005 times 9810, 0.4 meters. Okay, this is in Newton per cubic meter, to be divided by 4 meter, 4 cosine of 80 degrees. So sigma here is, okay, I will just use the previous solution and replace the theta by 80. So the sigma is 28.247 Newton per meter. Okay, this meter will be cancelled out. Okay, Newton per meter. That's your surface tension. Okay, so that's the end of this lecture.